Hello everyone. Let's begin the second lecture session on sequence and series. In the first lecture session, we have seen what is a sequence, and then we have also seen what is a monotonic sequence and bounded sequence. As we continue our understanding of sequence, in today's lecture session, we will see some more examples on monotonic and bounded sequence. And then we will proceed to understand the concept of limit. And next, we will see the concept of convergence or divergence of a sequence. So, before we begin to see the examples, let us recapitulate what was a sequence. Informally, a sequence is just a list of numbers written in a specific order. And mathematically, we have defined sequence as a function whose domain is the set of natural numbers. And also remember that we will be dealing only with real infinite sequence. So let's start with the examples. Determine if the following sequences are monotonic and or bounded. So we have here two sequences. Let us look into the first one where the nth term an is 2 by n square. Then clearly the n plus 1th term an plus 1 is 2 by n plus 1 whole square. And what we have to check here, we need to check that whether this sequence is monotonic and bounded. Now remember that in order to check whether a sequence is monotonic, we need to compare two consecutive elements or terms of the sequence. That is, we will compare an and an plus 1. Now see that obviously n is less than n plus 1 and therefore n square is also less than n plus 1 whole square. Now if we take the reciprocal of these terms and also multiply by a 2, we can easily see that 2 by n square is greater than 2 by n plus 1 whole square, which otherwise means that our an is greater than an plus 1. So therefore, the sequence is a decreasing sequence and hence it is a monotonic sequence. Next, let us proceed to check whether the sequence is bounded. Now notice that the terms of this sequence are all positive. Our an was 2 by n square, right? And therefore, we can say that the sequence is bounded below by 0. Further, note that it is a decreasing sequence, which we have already proved. So the first term will be the largest, and thus the sequence is bounded above by the first term, which is nothing but 2. So therefore, an actually lies between 0 and 2 for all n. Therefore, we can easily conclude that the sequence is a bounded sequence, and final conclusion is that the given sequence is both monotonic and bounded. Let us proceed to the next example where an is given to be n by n plus 1. Then an plus 1 is of course n plus 1 by n plus 2. Now, in order to compare an and an plus 1, let us find out their difference. So an plus 1 minus an will be given by n plus 1 divided by n plus 2 minus n divided by n plus 1. As we try to simplify this expression, we see that this is equal to n plus 2, n plus 1 we will have in the denominator, and the numerator will be, you see, n plus 1 whole square minus n multiplied with n plus 2. So this actually gives just 1 by n plus 2 multiplied with n plus 1. Now obviously this quantity is greater than 0. So therefore we can conclude that an plus 1 is greater than an. And this now confirms that the given sequence is monotonic increasing. Next, to check whether the sequence is bounded or not, let us observe that because this is an increasing sequence, the first term of the sequence must be the smallest term, and hence the sequence is bounded below by a1, and notice that a1 will be 1 by 2, or rather half. Also, note that since n is always less than n plus 1, an is less than 1 for all n. Thus, for this sequence, see that an lies between half and 1. So therefore, of course, this is a bounded sequence, and then finally we can say that the given sequence is again both monotonic and bounded. Now we proceed to understand the concept of limit for a sequence. Now, all of you are aware of this concept of limit when you have studied functions. And please remember that we have seen that a sequence is nothing but a function. So we can now try to understand how we can define the limit of a sequence with this pre-knowledge. And why do we need to understand this concept of limit for a sequence? Now see that we are dealing with infinite sequence, and therefore it is a natural question to ask that what happens to the terms of the sequence as n approaches infinity? Whether the term remains finite or becomes infinite. So this is why it is important to understand now the concept of limit of a sequence. Now, to understand this limit of a sequence, let us try to draw the graph of the sequence n plus 1 by n square as n goes from 1 to infinity. We will here actually plot n versus an. So, what will be the points of the graph? The first few points will be as shown here. How do we get them? See that as n equal to 1, an will be 2. If we take n equal to 2, a2 will be 3 by 4. As we take n equal to 3, an or a3 is going to be 4 by 9. So like this, we can generate the points of the graph to be plotted. So now, if we plot the graph for the first 30 terms of the sequence, it will look something like this. Here is the graph, right? So, what do you observe from this graph? We can easily see that as n is increasing, an is tending to 0, is approaching or becoming smaller and smaller, and is going closer and closer to 0. So this is a situation where we say that 0 is the limit or the limiting value of the sequence, and we write limit an as n tends to infinity is equal to 0. So with this understanding of limit, we will move forward to see the formal definition of limit. First, let us look into the definition of limit of a sequence when the limit is finite. Thus, a sequence an of real numbers is said to tend to a limit L if for every epsilon greater than 0, there exists a positive integer capital N depending on epsilon, such that modulus of an minus L is less than epsilon whenever small n is greater than capital N. What does this mean? This essentially means that whenever small n is greater than this positive integer capital N, the member an of the sequence is very close to this number L. And smaller the value of epsilon, obviously an is more closer to L. So we write in this case limit n tends to infinity is equal to L, or otherwise we say an tends to L as n tends to infinity. Next, let us look into the case when the limit is plus infinity. A sequence an of real numbers is said to tend to the limit plus infinity if for every positive number m there exists a positive integer n depending on m, such that an is greater than capital M whenever small n is greater than n. So this essentially means that whenever small n is greater than capital N, the member an of the sequence is greater than this positive number capital M. So in this case we write that limit n tends to infinity is equal to plus infinity, or otherwise an tends to plus infinity as n tends to infinity. Next, we will look into the case when the limit is minus infinity. A sequence an of real numbers is said to tend to the limit minus infinity if for every negative number m there exists a positive integer capital N depending on m again, such that an is less than m whenever small n is greater than capital N. So this means that every member of the sequence starting from an, where this small n is greater than capital N, the member will be always less than this negative number small n. So in this case, basically what happens that an tends to minus infinity as n tends to infinity. And we write this as limit n tends to infinity equal to minus infinity. Now, with this knowledge and definition of limit, we will define the convergence or divergence of a sequence, which is a very, very important concept in the study of sequence. So, what is that? A sequence an is said to be convergent if the limit of the sequence exists and is finite. That is, limit n tends to infinity is finite. Say for example, we have the sequence an where the nth member an is 1 by n. Now obviously we can see that in this case limit n tends to infinity will be 0 because an is 1 by n. So the limit is finite and therefore we can say that this is a convergent sequence. Next comes the definition of divergent sequence. A sequence an is said to be divergent if the limit of the sequence is not finite. That means limit n tends to infinity is either plus infinity or minus infinity. So the examples are here. Firstly, we take the example of the sequence of natural numbers. That is, our an is equal to n. So it's quite obvious that as n tends to infinity, an also tends to infinity. And therefore, we can say that this is a divergent sequence because the limit is not finite. In the second example, an is minus n. So as n tends to infinity, an tends to minus infinity. And therefore, this is also a divergent sequence. Now, there can be a third kind. It may happen that the sequence is neither convergent or divergent. In such a case, we say that the sequence is oscillatory. So, what are the examples? See that the sequence with the elements 1, 0, 1, 0, dots 1, 0, that means 1 and 0 comes alternatively. Here, if we try to find the limit of the sequence, now see that an is not unique over here. An can be 1 or 0 depending on n is odd or even. So therefore, this sequence doesn't have any limit because limit is always unique. Even obviously the limit is not infinite also in this case. So this is the case of a oscillatory sequence, and we will see that this sequence oscillates finitely. The second example, we take the sequence AN, where AN is given by minus 1 to the power n minus 1 n. So if we write explicitly, we see that the members of the sequence goes like this: 1, minus 2, 3, minus 4, and so on. So here again you see that the nth member an, which is minus 1 to the power n minus 1 n, varies in sign depending on whether n is odd or even. If n is odd, then an will have a positive sign, and if n is even, then an will have a negative sign. So here also this sequence cannot have any unique limit, and in this case we say that the sequence oscillates infinitely. With these ideas of convergence or divergence of a sequence, we will close today's session. In the next lecture session, we will see some important theorems and properties on the convergence or divergence of a sequence. So, thank you and goodbye till then.